In this video, we're going to determine the minimum distance between um, two moving objects in 3 dimensions. We have Skippy flying an airplane that's currently right over his house. His altitude is 4,000 meters and his velocity is 60 kilometers an hour due north. At the same moment, Charmaine's 20 kilometers due west of Skippy's house. Her altitude's 2,000 meters and her velocity is 30 kilometers an hour due east. Charmaine's climbing at 50 meters per minute. We want to know at what time the planes will be closest together and what the distance will be. Well, much like a distance question in 2 dimensions, we're going to determine coordinates for each of the moving objects as a function of time. So we're going to say that east and west movements along the x-axis, north and south movement is along the y-axis. Movement to the east will be positive, and movement to the west will be negative. Movement to the north will be positive, and movement to the south will be negative. Now, the added dimension of this question is literally an added dimension. We have movement along a z-axis. So what we're going to do is think of the ground as having a z-coordinate of 0, and movement up being positive along the z-axis, and movement down being negative along the z-axis. Instead of each point being an ordered pair, each point will be an ordered triple. We need to determine our units of measurement with respect to both distance and time. Now, distances in this question are measured in kilometers and in meters, so let's use meters to measure distance, and time is measured in both minutes and hours, so let's use minutes as our unit of measurement for time. I typically like to pick the smaller measurement unless there's a reason not to. Now we're going to find a useful position to be the origin. Let's pick Skippy's house. So Skippy's house will represent the point 0, 0, 0. And now Skippy's initial position with respect to east and west is x equals 0 because he's right over his house. And his initial position with respect to north and south is y equals 0, again, because he's right over his house. But his initial position with respect to altitude is z equals 4,000 because he's 4,000 meters above his house. So Skippy's initial position is going to be 0, 0, 4,000. Now, in this question, he does not move east or west, so his x-coordinate will remain unchanged. He doesn't increase or decrease his altitude, so his z-coordinate will also remain unchanged. His y-coordinate, however, will increase as a function of time because he's moving north. Now, we have 60 kilometers per hour. 60 kilometers times 1,000 meters per kilometer is 60,000 meters. So instead of saying 60 kilometers per hour, we'll initially think of that as 60,000 meters per hour. Now, if we're going, we don't want to measure in terms of hours if we've agreed previously to measure in terms of minutes. So we're going to convert 60,000 meters per hour to 1,000 meters per minute. And so Skippy's y-coordinate will be increasing at that rate. And so we're going to be able to say that Skippy's position at any time t will be 0, 1,000 t, 4,000. Now, Charmaine begins 20 kilometers west of Skippy's house, so her initial x-coordinate will be negative 20,000 meters, negative 20,000. Now, she's neither north nor south of Skippy's house, so her initial y-coordinate will be 0. And she's 2,000 meters. Charmaine's altitude is 2,000 meters, so her initial z-coordinate will be z equals 2,000. So we see her initial position at time t equals 0 is negative 20,000, 0, 2,000. She's moving 30 kilometers per hour due east. That means her x-coordinate is increasing. Well, 30 kilometers is the same as 30,000 meters, so she's moving 30,000 meters per hour. Well, 30,000 meters per hour is the same as 500 meters per minute. So her x-coordinate is actually increasing at the rate of 500 meters per minute. Since her initial x-coordinate is negative 20,000, therefore her x-coordinate at any given time t will be negative 20,000 plus 500t. We'll just convert that to 500t minus 20,000. Now her y-coordinate never changes, so it stays constant at y equals 0. Her z-coordinate is 2,000, and it's increasing at a rate of 50 meters per minute. So we can say that her z-coordinate at any given time t is 2,000 plus 50t, meaning that ultimately her x, y, and z coordinates as a function of t are given at the bottom of your screen in red. Now we want to determine the value of t when those 2 points are closest together, and thankfully the distance formula for distance between 2 points is very comparable to the distance between 2 points in only 2 dimensions, and the formula is actually given on your screen there. It's the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared plus z2 minus z1 quantity squared. So using Charmaine's x, y, and z as x2, y2, z2, and Skippy's x, y, and z as x1, y1, and z1, we get the formula as shown right here. That is the formula for distance at any given time between the two. We do a little simplifying at the bottom. Then in the next slide, all we do is we expand out what's underneath the bracket, what's underneath the square root sign, and we simplify. And we have a formula next to that third check mark for the distance at any given time t between the two. Now, we're not going to actually do a domain analysis in this video, so we'll ignore that. So we'll ignore this domain right here. And what we're going to do is just say we have a distance formula given here, converting it to a form where it'll be a little bit more convenient to do the power rule. Setting that first derivative equal to 0 means that using the chain rule, we get this equation right here. In the next slide, we're just going to convert that to fraction form. Now we're going to multiply left and right side by the denominator on the left, and that leads us with 2,505,000 t minus 20,200,000 equals 0. Solving for t, we see ultimately that t is roughly equal to 8.064. So that's the time when they're closest together, but we would like to know the distance. So we just plug 8.064 into our formula, and we have 17,960 meters as the distance between them at that time. And so based on all that information, we have the time when they're closest together and the shortest distance in between the two planes.